Hello, good evening, all my friends. I'm Girish Dravid from Sterling Engineering Consultancy Services from Mumbai. Today, my topic will be one or two couple of case studies in steel construction, and one of them will be actual um, uh, description of a project, technical description, and the second one I don't want to talk right now. We'll come to that stage and you will know what it is. So just to tell you something about our company, uh, Sterling Engineering has been sort of indulging in structural steel construction works for many and various large scale iconic projects all over India and abroad as well. All of you might have seen this in Indira Gandhi Indoor Stadium at New Delhi. I think in the first webinar by our chairman Kamal Hadkar, he had dwelt on this structure as well. A very beautiful structure, symmetrical one with 8 pylons and a beautifully crafted space frame. Turbe railway station at Mumbai, Navi Mumbai. IMAX Dome again at Mumbai, the first of its kind in India when it was constructed. A 16-meter cantilevered canopy for Peninsula Business Park in Mumbai, and some composite column construction as well in the main buildings. The city, the Crossroads 2. This is a multi-use structure in Mumbai at Nariman Point, partly done in structural steel. You can see the framing plan, big girders, floating columns, and very complex structure. You can imagine the use of different grids at different levels, commercial, then parking structures, and on top Inox and other theaters, very difficult to construct and design as well. National Sports Complex, NSCI at Worli. The very first use of composite columns in Stock Exchange building at Mumbai, again, Dalal Street, very famous icon, everyone knows it. ICICI BKC, again, large scale use of structural steel and composite columns. A beautiful blend of Victorian architecture and composite construction in Mumbai again, that is ITC Grand Maratha. Some office buildings you can see, Sunshine Tower at Mumbai, again composite columns using concrete filled tubes, eccentric core, very challenging structural configuration for a tall building. Involving shear core at one end and structural steel bracings on the opposite end to reduce the torsion. Some pictures of Sunshine Tower. Connection details. We tend to give very simple connection details so that the behavior of members is can be easily assessed and implemented as well. So it looks beautiful with all those structural cross bracings. JK House, composite columns again, and some floors in structural steel framework. Again, very well-known iconic structure in Mumbai, Antilia, Ambani's residence. Office buildings for India Bulls. So all these structures I'm showing you just to establish our credentials in structural steel design and construction. This is a very large project, Dhirubhai Ambani Convention Center and Exhibition Center at BKC. almost 30,000 tons of structural steel has been used. Very large exhibition hall is almost complete. Now, having shown you some beautiful projects that we have done in structural steel, now I come to the case study, technical case study of ICICI regional headquarters at Hyderabad. This is a building. Almost 10, 12 years ago, we started designing this project, and it's complete now. It has been occupied. It's a very big building. The picture may not show it that way, but if you see the statistics, the building itself is almost 300 meter, precisely 285-meter long and 64-meter in width. That's a typical floor dimension. The basements are almost abutting the plot size, which is 300 meters by 80 meters. 3 basements, 4 podium levels, and 12 typical floors. It's at Hyderabad. These are the consultants involved. Hafiz contractor was the architect, and L&T ECC was the civil and structural contractor. Overall project size was almost 42 lakh square feet, and the client had given us a brief. The project had to be completed in 18 months. So naturally, after a lot of discussions, we compared various structural schemes, RCC, post-tension slabs, and steel, and so many. We came to a configuration which was really composite in nature. So basements and podium slabs were decided to be constructed in RCC, concrete. And by the time we came up to the fourth podium level, sufficient structural steel would be fabricated and ready for erection. Although the columns had to come from the foundation because they were composite. The rock excavation itself was expected to be completed in about 5 to 6 months, and then another 3 to 4 months for RCC and PT slabs for basements and podiums. And then the superstructure, typical floors, had to be completed in 9 months. So naturally, we had to tap the potential of structural steel as a material for quick construction. So excavation was done in 3 parts, so that when one part of the basement is ready for casting the footings, we plan to erect the steel columns and go up on one side, and the remaining 2 parts followed one by one. So that sequence was carefully drafted with the help of CBRE, the project managers, and we also decided to issue the drawings in the same manner. In addition, the contractors suggested taking the lift and staircase course ahead of the typical floors. So by slipform technology, the cores were taken ahead of steel erection by about 2 to 3 floors. Provision of insert plates was done for receiving the steel beams at a later stage. Couplers were provided for concrete junctions to screw in the reinforcement. And it was expected that for such a large plate, about 10 to 15 days floor cycle would be achieved. Columns were erected for 2 to 3 floors at a time, so that you will see some pictures later on. Columns stood for 3 floors, and then beams were connected at various levels simultaneously. Deck sheets were laid, and deck slabs were designed as if they were not propped, and so all that time of staging and supporting the deck sheets was eliminated. So in a sense, this huge a building 40 lakhs, 42 lakhs square feet, it had to be completed in 18 months. So all such measures in consultation with project managers and contractors, uh, all these ideas started creeping in, and we made a lot of good use of it. Typical floor construction was slab cycle was pegged at 6 to 7 days, which was an achievement in itself. Uh, in the footings, we had normal RCC footings, step footings, and again, you can see some ideas, a crystalline method waterproofing, so that that activity time is saved. All such things were imagined and implemented. Now, just to see what is the structural system for this building. The building, as I said, it's enormous, almost 285-meter long, 64-meter wide. And the complexities involved can be judged from what I'm showing you now. There are atriums, 3 atriums in the building. And there are a lot of cantilever slabs, and typical grid was almost 11 meters. So we quickly calculated the secondary beams, which are not frame beams, and which we are going to repeat thousands of times. And there was real optimization involved. They were placed at 3.55 meters center to center, UB 457. Deck slab Confloor 80 was used, and it was imported from UK, from Chorus at that time. And then the main frame beams, UB 610, 229 kg per running meter. And all this, the number of beams in a bay, secondary beams, the main beams, all those numbers, the number of columns to be erected, the number of deck sheet panels to be laid, all this was calculated to suit the estimated cycle of 6 to 7 days. Lateral load resistance was achieved through those large lift banks, core walls in the central part, and there are service lifts and staircase cores on the perimeter. Brace frames are also provided so that the additional lateral resistance was achieved. The length of the building is almost 270, so naturally we had to provide separation joints or expansion joints, as you can see. And the building was divided into 3 parts. So each part separately had to be laterally stable. So these lift cores, which were distributed, you can see some part of the lift core is going into the neighboring block. So these lift cores for the first and third blocks, they were eccentrics. So we had to use these outer cores, staircase cores, also as the lateral load resisting system. Although only 3 cores are marked, all the staircase cores were used as lateral systems, and the steel bracings on the other side, again in all the 3 blocks. So this comprised, all this created that lateral load resisting system effectively. Almost 100,000 cubic meters of concrete was used, and you can see the ratio. The reinforcement ratio, 20,000 tons for a lakh of cubic meter of concrete. It's not much, but that's because we use the deck slabs, a very thin layer of concrete, and almost no reinforcement in the deck slabs. So that's why the reinforcement ratio is quite less. But at the same time, structural steel, almost 22,000 tons was used. So these are some of the numbers. It's a gigantic project, but our ratios were quite in proportion. Now, although the image showed a box-like structure, there were many design challenges. In the lobby itself, front lobby, almost 2,000 square meters of column free space was required. Our architect, Hafiz contractor, if we give him the uh, liberty to design, naturally such challenges are expected. And height of the lobby was 16 meters, almost 4 floors. And above 4 floors, the normal office building had to be supported. Naturally, there were transfer floors and transfer girders, floating columns, and the girders spanning, I'll show you the plan. This is the lobby plan. The main girders are spanning 33 meters and the secondary girders are spanning 21 meters. So this is the plan of the front lobby where these girders are highlighted. See the picture. And if you just want to see the scale, look at those human figures at the bottom and how high the lobby is. This is that 2,000 square meter lobby that we are talking of. This is the framework, and the transfer girders themselves were 3 floor deep. And it's easy to uh, create such transfer girders in steel. Imagine what could have happened if this was in concrete. Uh, so these diagonal bracings, although they will be seen in the facade, if you go to that building and see outside from the internal office space, they look beautiful. So we all structural engineers think the steel sections going here and there, diagonal, vertical, they look beautiful. Even Hafiz contractor thought so. He never complained about diagonal bracings. On the right hand side, you can see a cantilever bracket, and the cantilevers were supported on such brackets at every 6th floor. It's all, there is no limit to architectural imagination and how you treat these bracings, diagonal bracings. Mind you, these bracings are there inside the offices as well. And Hafiz has done excellent job interior wise as well to use these diagonal bracings very aesthetically for internal spaces as well. This is a picture for showing you how the girders were erected. You can see the bracket at the top of the girder to support the floating column, which was wider than the top chord of the truss. Otherwise, people are busy splicing the diagonals and verticals of the trusses. The truss was erected in pieces of naturally. This is another picture showing the main transfer girder, which was 33 meter long. The complexity was again enhanced with the presence of these tree boxes in the building on the facade. And it can be clearly seen that these tree boxes are actually spanning across the expansion joints. You can see the diagrams on the right hand side. So it was a very tricky situation, but we had to come up with some very clever connection details, pinned and rolling roller details on the other side. And these trusses were connecting the two blocks across the expansion joint without sacrificing the concept of that expansion joint. Not only the complexities in due to architectural concepts, but during the construction itself, there was a change in design brief. Building was initially designed for 22 floors, and suddenly it was told to us that the building had to be now only 17 floors. And some cantilever extensions had to be provided to accommodate that FSI loss because of reduction in the height. Somewhere those atriums had also to be covered up to gain that area, lost area. So we had to bridge the atriums with actual bridges or there was an atrium in the rear portion where a guest house was introduced. So another round of design and more transfer girders to float the columns of the guest house, which had different grid than the original grid of the building. And then there was another brief that the material which was procured for 22 floors was to be used in the same building. All the material was not procured, but some material for columns was procured right to the terrace. Now that excess material, which was not going to be used in the 17-story building, that had to be converted to usable set of sections which could be used in 17-floor building. So that was another challenge, and we used a lot of material, most of the material which was procured. Two new lifts were introduced. That the guest house building was planned with RCC because the more number of floors had to be accommodated in lesser floor height. At the same time, podium slabs had come up to certain level, and we had to introduce the steel girders to support this guest house. So a lot of complications. A service floor was required to divert the services of the guest floor and hotel rooms. And this is the plan where you can see the additional highlighted, those are the girders, and floating columns can be seen which are not on the main grids. So this was an addition to the building. The floating, the transfer girders for the floating columns. Constructionally, as I mentioned earlier, the columns were erected for 2 to 3 floors at a time. Very nice picture this is. On the right hand side, you can see some deck sheets being erected. Probably they will be cast also. The concrete will be poured on top of them, while at the lower levels, the beams are still being connected. Very telling picture. This is a detail how the reinforcement was tied around the structural steel beam column. The transfer girders were erected in pieces because they were huge, spanning 20 and 30 meters. Lifting erection was a big challenge. Again, transfer girder erection. You can see they are tied also with cross ties, temporary cross ties during erection so that they don't topple over. Splice joints for the transfer girders. These are at the fourth level in the lobby. Typical splice joint detail. The bracket that we talked of. The transfer girders for the guest house. And these are some typical details that I'm showing you now. The step footing. The structural steel column was erected on the first step of the footing. The reinforcement of the encasement was, the whole idea was the reinforcement of the encasement should not obstruct, or the steel column should not obstruct the reinforcement. Now in this picture you can see the reinforcement is clearly outside the base plate also. So thereby the fixity for the reinforcement and the structural steel column both were achieved together. The column splice detail, we intentionally went in for the splice plate detail for web and flanges differently. And generally there is a practice of having a end plate, face plate connection for composite columns. But we thought of doing this because we had a doubt about the quality of milling that would happen for the face plates, the contact area between two face plates uh, was a concern for us. So we went in for this splice plate detail. This is a detail for creating bearing and shear connection for the flat slab. As we discussed earlier, the slabs for podium and basements were flat slabs, post-tension flat slabs. And the reinforcement could not pass through the composite column where the steel section is present. So we had to create a bearing and also the shear connection. This partially completed uh, beam column connection detail with a small bracket stiffener plate at the bottom. This is a moment connection, as can be seen with a plate on top of the beam as well. The bracing connection. Bracing connection with stiffeners, because these braces were A-type braces at some places. So they were joining the midspan of the beams. This is the bracket, peripheral bracket to support the cantilever projections. This was provided at every sixth level. The execution was very dramatically done, in the sense this is a very good picture where you can see deck sheets erected at various levels. The beams have been erected at many levels. The columns are going up. They are not yet encased, but all the preparatory work has been done, and the deck sheets are waiting to receive the concrete. And concreting is not the critical item in the construction cycle. Very fast construction practice adopted. This is the deck sheet with studs. In those days, 10, 12 years ago, the gun welding was very rare, and we used it for the first time, as we know, to fix the deck sheets to the beams below. Almost no reinforcement was used in the deck sheets. Only concrete was poured, and Chorus told us about fibers to be used in concrete, which could help reducing the shrinkage cracks on the deck slab concrete. Reinforcement was used only for the cantilever part of the deck slab, whereas at bottom there was no reinforcement. At some places, although you can see here, there was a requirement of reinforcement on the top. This was mostly done where there were heavy loads and double mesh was used. This is a right-hand side picture, shows the finished floors just above the lobby, and that inclined facade, glass facade. It's actually an internal facade. You can see the partially finished bracings. They are clad and architecturally very well treated. And if you go there today, they look, the space is just beautiful. It has some different kind of ambience. This is a very dynamic looking picture, a night shot of the construction in progress. And someone just told me that this picture is looking more beautiful than the completed building, because it shows all the beauty of structural steel construction in action, cranes and all the bracings, trusses clearly seen. So that was a presentation, technical presentation for the ICICF building. And while we are doing so many buildings in steel, and we have gained a lot of experience, so I have jotted down some points which might be useful. Where do we use structural steel? we use mostly in composite columns, transfer girders, outriggers, long span roofs, canopies, mezzanines, industrial structures, bridges and skywalks, facade, equipment platforms. So this is where structural steel is mainly used. In tall buildings nowadays, of course, there have been buildings where there is a major use of structural steel in flooring as well. But these examples are quite rare even today. So, as I say, there is although we talk of structural steel in I mean, many times there are seminars, webinars, and a lot of discussion goes on. In our company, almost for every project, we uh, create an option of structural steel, present it to the client, discuss pros and cons, and this screen shows advantages of using structural steel like reusability, accuracy in fabrication, saving construction time, easy dismantling, recycling, all this we tell the client. At the same time, we tell them about the disadvantages of using structural steel as well, which are really not disadvantages in using structural steel, but in the process. Uh, the cost definitely is higher, overall higher structural cost. There is an early investment. You have to freeze the designs. The changes should be avoided as much as possible because you already invested in the material. Material has been procured, and whatever you procure should be used as it has been designed. Storage, once you procure that material, there has to be a lot of storage space somewhere near the site. Uh, because beams, the construction involves beams and columns, the headroom is always an issue. Uh, since we are dealing with linear elements, there has to be a discipline in architectural planning as well, not only structural. Uh, most of the times, if you are going to develop a building and sell it to customers, you might have to finish the building to avoid showing the decks, ribs of the deck slab, so many things. But all these pros and cons we discuss with the client, and most of the times, client is convinced about other things time and all those things. When it comes to cost, there is a problem, and the naturally the balance goes in favor of concrete. Probably that uh, time factor, although client understands that time is also money, there is financial cost involved, but ultimately the overall final cost wins in most of the cases. This is one real example we from a building tender which we designed as a composite building. You can see that structural steel cost was more than 50%, and reinforcement, formwork, concrete, fire protection, deck sheets, they constitute the remaining 45%. Although you might say that fire protection and deck sheet is also associated with structural steel construction. So if you add those also, almost 70% of the cost goes in structural steel and its associated materials. I'm not showing this to discourage you people from using structural steel, but what I'm going to show you now is a live example of an optimization exercise that I did with a contractor. Uh, Before that, when we talk to the client, and even for this case study, we discuss with the client and the contractor that in order to use more and more steel in buildings, it is not necessary to insist on total steel solution. It's not necessary that your columns, beams, and deck slabs and bracings, you go for a total solution, steel solution. You can have a composite building wherever you can see advantage of using steel, use steel, otherwise stick to concrete. It is cheaper. The technology of pouring, manufacturing, placing, pouring, vibrating concrete is absorbed in our construction industry. Anyone can do it. Whereas the steel construction requires a lot of training, expertise, um, a lot of resources like specialized equipment, trained welders. So if we are not confident about going for steel construction, we should not indulge in it. Leave the difficult part to expert people, steel contractors. If they are being costly, minimize their usage, but use steel to such an extent that you derive full advantage of using structural steel, as we had discussed earlier, the time saving and all other things. So identify key areas where steel scores for RCC in terms of ease of construction, speed of construction, repetition of member lengths and sections, composite columns, etc., etc. So having done this, uh, what are the low success rate that is present uh, to convert a project into steel structure? This starts from the tendering process itself. There are competitions. First is the architectural design. When an owner or a client decides to launch a project, first thing that he does is he approaches an architect. Architect, without thinking of the structural system or rather the structural construction material, comes up with a space plan and an elevation. And this is most of the times regardless, giving any due regard to the structural design or MAP design, nothing. So it's basically a visual uh, what you can call visual appeal, which appeals to the client, and it's like a monument. The client evaluates 3 or 4 different elevations and space plans. That is the first competition. Then the next person to be called in is the liaison architect, and he advises the architect and the owner whether that plan is can fit in the regulations, local DCR and all that. After that, after all those things are taken into account, the plan gets developed in a very different way, very what do you call uh, indisciplined way, so to say, if architect has not thought about the structural system, and then a structural designer is called in. Now, the talk starts whether it is in concrete or steel. The structural designer then takes a look at the architectural plan, tries to draw some disciplined grids here and there, and decides whether steel can be used. If the grid is not regular at all, there is no option but to go for RCC. If there is some semblance of nice parallel grids in both directions, we can think of structural steel. Then we can also do an alternative or option study and tell the client this costs so much and that costs so much. So then client naturally says, okay, work on both the options. The poor structural engineer comes up with lot of comparative data, and it mostly involves the cost. There is no discussion about the method of erection, method of construction, time schedule. All this is not discussed at this stage. So once the structural engineer prepares BOQs, RCC and steel, the contractor is called in. If the decision is already made about RCC or steel, the contractor is asked to quote for that particular system, or contractor quotes for both, or different types of contractors are invited. One uh, person who is expert in RCC, he quotes for RCC. Another agency which has done a lot of steel buildings, they quote for steel buildings. So there is no method in deciding, the comparison is not at par. At that stage, even the drawings are not fully available. We don't know what kind of resources the contractor has. And we just give the structural drawings and architectural drawings to the contractor and ask them to quote. The RCC and steel packages are tendered separately if there is a composite building involved. So all this results in getting a very unfair price for the building. And this is a general bar chart where pre-construction activities are given a very short time, and this chart shows activities up to fabrication drawings for a steel building. Now, I had done one building, 34 floors, actually two towers sitting on one single podium in Delhi area. I'll just show you through what stages we went in to arrive at the final construction cost. So this was a 15 lakh square feet building in near Delhi, Noida precisely, 155-meter tall building. Original scheme was RCC, foundations, raft, retaining walls, shear lift walls, and columns were considered to be composite. Beams at all levels would be steel and laid over with a deck sheet and concrete. So this was this was the client's brief, in fact, and this was the scheme with which the client's consultant had put out the tenders. The contractor who was bidding for this, he came to us, and then we sat on the scheme. Fortunately, the consultant and the owner gave us complete freedom to change the system the way we want in order to optimize. That was a reason why we could go through this entire process of optimization one by one. So this is a general key plan. In this particular presentation, I'm not showing you anything technical. I'm just describing the procedure through which we went in to optimize the building. So in the first version, as I said, composite columns at all levels, which are marked in pink. The shear cores, the yellow ones, they are in concrete as well. Retaining walls marked in green, they are in concrete, but all the floors marked in pink, they are steel beams. First of all, with the discussion with the contractor, we discussed the number of secondary beams to be provided in a typical bay, because contractors told us that his cost doesn't necessarily depend only on the material quantity, material weight. The number of beams that he has to lift and erect in place matters a lot. The craneage, they call. So we did this preliminary exercise, one beam in the bay, two secondary beams or three secondary beams. This is the ETAS model we did. So we did a thorough study, analysis, and design at each stage for the entire building, including the earthquake and wind analysis. Everything was carried out. We went up to detailed quantification and came up with this sheet. And you can see, again, I'm not going into the numbers, but see only the last number. The total structural cost came to 1,360 rupees a square foot. Now, this involved concrete for plumb concrete for leveling PCC, retaining walls, foundation, raft, encasement concrete, just the scheme that was put forward by the owner's consultant. And of course, structural steel, base plates, columns, beams, bracings, connections, etc. So 1,360, you can remember this figure. But when this figure came out and contractors people worked out their own cost, it came to 1,530 rupees per square foot. So this is the difference between the cost calculated by consultant, that is us, and the cost worked out by contractors, procurement team and project team. What was the difference? The difference was we had used 460 grade steel, and the market rate for 460 grade steel was quite high. It was not available at that time. So it was selling at higher price. The contractor suggested use 350 grade. We used 350, checked the quantities, and we saw that using more steel, because the grade is now less, we had to use higher sections. Even then, the cost of steel was coming lesser. He again gave us the feedback that self-compacting concrete is costlier. So quality will be assured with normal concrete as well. This is the assurance given by contractor himself. So fine, no problem. Then the rate of fire protection assumed by us was less. He produced actual quotation received by him from the vendors. He also produced actual quotation received from vendor for the deck sheets. So all this together, as against our 1,360 rupees, his cost came to 1,530 rupees. So he suggested all these 7 measures to reduce the cost. So what was that process? So steel contractor told us, my client, I mean, who had appointed me, he was the design and build contractor, and I was his consultant, designer. So he told me that cost is not only material, but purchase, import, and transportation of the material from wherever it is available, fabrication shop overheads, storage, that costs, storage space costs, equipment, energy and water, labor, supervision, technical staff, shop management. He had all these figures on his fingertips through his previous experience on his other jobs. Then site erection overheads, storage equipment, all those things. Overheads, environment. This environment is not your normal weather and all that. Knowledgeable people will know what environment is. Then insurance and commissions and markups, etc. Then taxes. So all these things we consultants don't know. We just go by some figure that, okay, structural steel would cost a lakh of rupees per ton, including everything. But no, it can change. And a contractor who can be our friend, if he is our friend in our team, he will actually tell us what could be the cost of material to be used in columns, beams, and deck sheets, and fireproofing, and all that. So our problems are different. Contractors' problems are different. Structural consultant will generally talk about codal provisions and performance criteria, deflections and accelerations. Then the steel building should actually function as a concrete building. We don't want beams being seen in the soffit of the slabs. All those things. Uh, I mean, we are under tremendous pressure to give a structural configuration the way architects and the owner wants, whereas contractors' problems are different. But if we come together, contractor and consultants, and if they are given free hand by architect and owner to, if the objective is to reduce the cost, there are many ways. One important point here that I mentioned is introduction of technology advances are almost discouraged in the tender stage. Whereas if the job is given to a contractor to be bid for a design and build project, contractor himself will come up with a lot of new technologies. He is ready to invest in new technologies in order to optimize the cost. This I have learned on many projects. But if we suggest something in the tender stage itself, the contractor will try to take advantage of it. Simple example is advancing shear cores in tall buildings. If we specify that shear course, lift course have to advance 3 floors or 4 floors higher than slabs, contractor will definitely charge a premium. But if you tell him to choose his own technology, he will select the same technology and probably give a discount because that is to his advantage. So in version 2 of that optimization, we followed all the suggestions given by the contractor, and now the concrete was used in the basements also. All 3 slabs up to the ground floor, you can see the green lines. Those were in concrete, rest all remained steel. Cores are still in concrete. Nothing has changed other than that. But steel grade had changed to Fe355 for all steel members. By doing this, again, doing all E-tabs and everything, all earthquake analysis, we came to a cost of 1350 rupees. Not much difference, right? But you can see all those figures in red, those things have changed. Naturally, the contractor is not happy. So another set of comments came from the contractor. Go for flat slabs in the upper floors also. No composite columns for substructure. Nominal embedment about 36 floor in tower A, where the loads reduce. Avoid structural steel section inside the columns. That was his suggestion. And concrete grade for column encasement and shear walls changed to M50 from earlier M60. Thickness of shear walls was changed to 600, increased. Spacing of secondary beams was changed to 2.67 meters instead of 3.33 earlier. So all this resulted in the next version. See the last one also, deck sheet thickness reduced to 0.8 mm as per design provided by the deck sheet vendor. So now he is not going with the design provided by us, but the vendor has provided him an optimized design. So this is the version 3 of that. And what is the change here? You can see the top four floors, the columns are purely RCC. We eliminated all the embedded sections there. And in this, we actually went to design the connections also. Earlier, we had assumed about 15%, over and above the material quantities as connections. But here we actually designed and quantified. And as I said, spacing of secondary beams was reduced to 1/3 grid, deck sheet design optimized. And now the cost came to 1238 rupees. So here the contractor was satisfied. He said, yes, this is the figure because it was coming closer and closer to the RCC cost that was estimated, which I'll show you later. But these are the comments from the third BOQ also. So the comments never ended until contractor was completely satisfied. So again, let's not go into this, but the graphic will show you what it is. So all concrete except encasement and shear walls changed to M35 now, which was earlier M50. Naturally, the column sizes increased, but it was okay. We went back to the owner and architect and they said it's fine. As long as the cost came down, it was fine. Columns and shear wall sizes increased. Reinforcement quantity actually reduced because we increased the concrete sizes also. So there was a double benefit here. And this shows that it's not necessary to go for a complete steel structure, but wherever possible, try to use concrete as well. Of course, depends whether it is possible to do it with the architects and owners. But now the cost has come down to 1203 rupees, almost 1200 rupees a square foot with all the changes. So these are the 4 cases from 1360 rupees to 1200 rupees per square foot. We did all this analysis. And 895, almost 900 rupees was the cost estimated for RCC building. So that much increase was acceptable to contractor as well as owners. So key achievements is we could save over the tender cost by almost 11.5%. Exercise completed in 45 days. It took 45 days for us to come to this. But here the cost was fixed for the owner for the given design brief. And I must commend the owner and architect to allow the contractor to use the changes. So I'll move fast now. So if owner had included architectural and MEP design in the bid process, flexibility in architectural shape and design was left with contractor, not always of course, but choice of finishing and cladding material was given to this alliance of architect, structural engineer and contractor. And uh, concept of pain share and gain share was introduced in the whole process. The process can become quite optimized. This is the message I want to give. So with this, I think I'm coming to the end of the presentation. If there are any questions, um, yeah, I can see that there is time only for 2 questions, and I already have 2 questions here. The first question is, in your presentation, you have shown commercial projects and sports stadia, etc. But what about residential projects in steel? Well, we have also designed a couple of projects in structural steel. I have particularly designed a tall building, 250-meter tall building in structural steel. Again, it's a composite building, but steel has been used. And there, the the developer is selling the premises with a pre-finished spaces like false ceiling and walling, and he's hiding the bracings in the hollows of the walls and all that. So that the trend is catching up. There are 2 or 3 more proposals that have come to us for structural steel uh, residential buildings. So people are thinking about structural steel in residential buildings as well. The next question is, oh, this is a very good question. It is possible to execute large scale projects with the help of larger contracting companies. However, when it comes to smaller projects, how do we ensure quality and efficiency? Well, we have been fortunate enough to work on very large projects and with very resourceful contractors, world-class contractors. So it was easy for us to design steel buildings the way we wanted, and we were sure that the contractors would definitely give justice to our concepts and designs. However, we have also worked with smaller contractors, local contractors, and I must say that their understanding of steel is equally good. They may not be as resourceful or uh, with large capital at their hand, but it's not that smaller contractors cannot work on steel structures. We have to just talk to that contractor. As I presented in my second part of the my presentation, we have to have a dialogue with that contractor, that agency. What kind of resources he has, what kind of expertise he has, and uh, we can tweak our structural designs or even architecture to come up with a beautiful product, building product. So it's not that only large contracting companies can build in structural steel. Any other question? Okay, so I hope you enjoyed my presentation, and I look forward to your questions to organizers. You can send emails to our organizers, and I'll be glad to answer them. Thank you very much.
Oh, it went off very well.